Hi, everyone. So this is the second lesson of our exponential unit, and this is Pert and Nert. You'll soon figure out why it's called Pert and Nert, just not today, tomorrow. So this is day one. We are on page 107. And again, our learning targets are going to be identify the domain and range of the exponential functions, investigate graphs of exponential functions through intercepts, asymptotes, which we haven't learned yet until today, intervals of increase and decrease, and behavior. The irrational number E, we're gonna slowly we will start investigating it, but we won't finish it until the next lesson. I know, can wait, right? Juno, this is the do now for today. Juno is opening her first savings account and depositing $100. The bank offers 3% annual interest to be calculated at the end of each year. So at the end of the calendar year, they will be paying Juno 3%, just to say, hey, thanks for loaning us the money or depositing your money here. So again, APR is something that you may have seen, like whether it's for loans or for cars or whatever. A really good acronym to know. APR is annual percentage rate. Okay, so annual meaning every year, annually, right? Percentage, so it's going to be some sort of percent, right? And then rate, this is how much they're charging, right? Or they're going to give, depending whether it's a loan or what is it called, or for interest, like at a bank, right? So here, this is going to be that 3%. So this is like that rate. The $100 is what we're starting off with. And if you remember right here, we have this y equals a times b to the x power. Remember, a was our initial amount. So think about, what is our initial amount? Yeah, it's $100. And same thing with our b, that is going to be our the multiplier. So what do we keep on multiplying, right? Oops. I said multiplying, I went multiply. All right, so first one is to write a function that models the account of the money in Juno's savings account after T years. So our time is in years. And again, our initial amount is $100. And then we're multiplying by 1.03. How do we get that? So that was a big question for some people. So remember, we have the initial 100%, right? The amount that Juno put in, right? It's not because it's $100, because we're going to keep the 100%. Like, we're keeping 100% of that money, plus we're adding on to it 3%, right? So that's why it has to be 100% plus 3, which would be 103%. And how do we write 100% as a decimal? It's just 1. And how do we write 3% as a decimal? 0.03, right? So altogether, that would be 1.03. So that's why it is 1.03. And again, to the t power. And then we're going to calculate that out for at the end of 1 year, and then at the end of 5 years, right? And so here's at the end of 1 year. Please make sure you're using your well, the first one, I guess you don't really need a calculator if you can do that in your head, right? You should get $103. And the second one is going to be, after you do put that in your calculator, you should get $115.93. So again, we're not taking $3. So every year it's not $3 that we get. That's not what we're talking about. We're taking 3% every year of that balance, right? So year 0 is $100, right? That's what we and then year 1. So after the first year, it's 103. So after year 2, remember, we're not going, oh, we're just not adding 3. Remember, we're multiplying by 1.03. So we're going to multiply this guy by 1.03. So that would be, get my calculator. Let's just use our calculator here. So this is going to be our 103 times 1.03, right? We want 3% more off of that. So it's 106.09, right? So that's going to be 106.09. So notice we're getting a little bit more than what we originally would have gotten, right? Just a little bit. We added 9 cents to that, right? So the first time we got $3, the second time we got $3.09. And so we're going to keep, that's why it's called compounding, right? So all that interest compounds, right? So we're taking this, whatever this balance is, and multiplying that by 1.03. Okay, so we're not taking it's 3% of 100, and we're going to just add that every single time. We're not doing that. Okay. So, because that would be linear. This is definitely exponential. So there we go. And this is literally what we just did. So this is like the basic equation for interest that is compounded annually, which is, you know, you get paid only once. I like to think of it as how many times you're going to get paid interest in a year. This one is only once. Okay. And then so here the P, which used to be our A, right? P stands for principal, right? That's the original amount. What's your principal? That means like how much you put in, right? Or how much are you taking out as a loan, right? Depending on which side you're on that. And then 1 is, remember, this is like your 100%, right? It'll always be 1 because we always want to keep 100% of what we put into it, right? And then we're going to add in our rate. So this is our interest rate. In this case, it was 3% or 0.03. And T, of course, is still time. All right. So that 1 plus the R, that's our B. It's our multiplier. All right. And this is what you should be doing for your homework. I would say exit ticket. I would try that next time. I mean, I guess you could do it. Yeah, you're going to have to do it next time because it does talk about stuff that we didn't get to yet. So we're going to skip into here. So we are on page 109. And we had talked about, well, what are some B values? Okay, so we're going to just strip down the equation to its bare essentials. Okay, so all we have is the B and the exponent. We don't even have A. Well, A is just 1. Okay, so that's why you don't see A here. It's just 1. We're going to just make it as bare minimum as possible. So now just looking at just the B, right? What can we multiply it by? Or what can B be? Can B be if we didn't want any growth or decay, right? We didn't want it to go up or go down, right? And we had said, well, I'll put it right over here. So I said, okay, so our A was, so we start with 1, right? What do we keep on multiplying by so that it stays the same? A lot of people are like, oh, you just multiply by 1, right? Because 1 times 1 times 1 is just 1, right? So yeah, so you will never see this. Okay, shouldn't say never. So you will usually never see this. See my modification? Because 1 is not fun. It's boring, right? Because if you just multiply everything by 1, did it change? Is it ever going to change? No, it's going to just stay as 1. It's not interesting. Okay, so this would not be called exponential because, I mean, it's not going to be a growth or decay. It's not exponential growth or decay. It's what I meant. All right. So what we're going to do here is we're going to think about, okay, well, how do we know how much it grows by, right? How do we know grows by? How do we know if it grows? Oh my goodness, it was a long day. Stay focused. All right, so what could B be so that it grows? That's what I'm trying to ask you. And we're like, well, it had to be like 2. We could do 2, right? 2 times 2 times 2, like it gets bigger. And we could do 3, we could do 4. And I guess the question is going to be like 1.1. Would 1.1 work? And people said, well, yeah, it could work. It'll just be really small and slow, but it'll still grow. Ooh, that rhymes, right? So 1.01 will still grow. It's just very, very, very slowly, right? Very slowly, right? But it's still growth. Growing is growing, right? So it'll look something like this. It'll be very slow to grow, but it'll grow. So anything bigger than 1 is growth. So then what about decay? So then this is where a lot of students said, well, B is less than 0 or less than 1, right? Anything less than 1 should be decay. And then, so this is where, well, what if it was -1 or like -2 even, right? So if it was -2, because that's still less than 1, right? What happens there? And negatives are weird, but interesting. So here we go, -2, -2, -2. So we know that 1 times -2 is -2. And then -2 times -2 is +4. So do you see it went from decay? So it went smaller, but now it all of a sudden went bigger. And then 4 times -2 is -8. I could write 8. Okay, do you see how it goes from positive to negative to positive to negative? So it's going to do this flippy thingy, right? And it's just very strange, right? So what it looks like is literally like this. Do you see this in the black? This is what it looks like. I know, it's crazy. I would rearrange this, but I'm scared that the dots won't put, this is what happens. See, the dots don't come back up again. I don't know why. It's very strange. But yeah, it does this thing like this, or was it like this for you guys? Yeah. And so it goes from positive to negative, and it's not continuous, right? So yeah, it's discrete for sure. So we're just can't be negatives, because negatives are weird. It doesn't give us this nice graph. So what can it be? And so some people said, oh, it's like a decimal fraction. Well, what kind of fraction? So anything between, because we're like, well, could it be zero? Right? Because what happens if it's zero? Then this will be zero, and this will be, so the whole thing is just zero. It doesn't even matter. It's just zero, right? So it can't be zero, because zero is, again, it's like one. It's not fun. And then so it has to be anything between 0 and 1. Can't equal 0 or 1, but it could be anything in between it. So some kind of fraction that's in between 0 and 1. That's decay. That should help you with your homework. So hopefully you're watching this before your homework. Hopefully you're doing your homework. That too. All right, and so our decay is going to look something like this. So it starts big and then starts getting smaller. That is usually the idea of decay, right? And then we're going to go pass through some of that. So we're on now page 110 on the bottom part. So just flip to the next page. And we are talking about the domain range. All of this, we talked about this in the learning, right? And so I just took these two graphs from your homework section, right? Maybe you recognize them. And we decided, we said that, oh, well, a lot of us said that this was going to be growth because, you know, see how always from left to right and it increases, right? So that's what we're going for. So this is growth, the one that goes down. So it goes down, dude, I don't know which way now. That's going to be your decay. All right, so let's take a look at the domain here. So the domain for growth, if you go, remember the domain is talking about the X values, right? So how far left and how far right do we have to go, right? And this is, and there's an arrow and it just keeps on going forever and ever. So this is, X can be anything. And if you look at it algebraically, it's b to the X. What could X be? X be positive or negative or zero, it doesn't matter, right? X, there are no restrictions on that. So it was from negative infinity to positive infinity. And then if you look at our range, that's about our Y values, right? How low does it go and how high does it go, right? Well, how low does it go? Look, oops, wrong one, the growth one, right? So how low it goes is, well, it looks like it doesn't go below 0, right? And if you look at our graph, so let's take a look. I used just 2 for our B because I needed a number. So if you look right here, and do you see how it looks like it's at 0? And honestly, if you put your point on there, see how it's 0.001, and it'll get small, and all of a sudden it just goes to 0 right here, right? This is actually not 0, because if you scroll in and you scroll in and zoom in and do you see? Not 0. It's above 0, is barely above 0, but still not 0, right? So this is the you're getting really close. So you're like the I'm not touching you thing, right? Like I'm not touching you. Right, and it'll never touch, right? Because if you can imagine, how would it be able to be equal to 0? Could it equal 0? That's the question. Because remember, what are we multiplying by? The exact same number every single time, right? Just like how we did up here, right? So if we're multiplying by, let's change this number. So if we're multiplying by, let's say, 2 every single time, like here, or even multiplying by 1/2, right? Every single time. Are we ever going to get to 0 if we cut something in half and half and half and half? No. Like what is the only way to get 0 when you're multiplying? Multiply by 0. But if you keep on cutting something in half and half and half, at some point, right, in real life, we'll have, like, it's just too small at that point, right? But theoretically, mathematically, it will never be 0. It'll be close to 0, but it'll never be 0. And that is, so at 0, it'll never, so the more we go down here, we won't, oops, made that way too long. So the more we go to the left, we'll never get to 0, but it'll get really, really, really close to 0, right? So what we're saying is that the range is from 0 to infinity, because as you can see, it definitely goes up, right? So it goes to infinity. But notice right here that it is not it is a parentheses, right? It is not a square bracket, because it can't equal 0. So right here at 0, where y is equal to 0, this is what we call the asymptote. The asymptote is like a fence, an electric fence that you cannot cross or even touch. It's just not going to happen, right? So this line will get really close to the asymptote, but we'll never get to the asymptote ever. Okay. So if you kind of think about it, then would that make it parallel lines? It's not the definition. Okay, but yes, but if you think about it, you're like, is it? All right, so horizontal, although they will look very much parallel, right? Because they look pretty much like, not like it's getting closer, right? But anyways, so this is what we call more specifically a horizontal asymptote, because it's horizontal. What do you think these are? Something to think about. So y is equal to 0 here, because that's what that equation is for that line, that dotted line right there. And the x-intercepts, what are the x-intercepts? Well, it's never going to hit the x-axis because the asymptote is the x-axis. So therefore, we don't have any, right? And then what is a y-intercept? A y-intercept, well, you have to ask yourself the question, well, what's b to the 0 power? Because remember, that's where the y-intercept is when x is equal to 0. And anything to the 0 power, if you said 0, sad days, go like this. I'm just kidding. That would just be 1, all right? Because anything to 0 power is 1. And if you don't remember about those things, go back and look at an exponent properties video. There we go. And then our actually, let's talk about the intercepts real quick. Does this mean that all exponential functions do not have the x-intercept? No, that is definitely not the case. It's just for this particular like basic, when we get to the basic, like this is like what it looks like in general. Okay, here, yes, because you can see it does not have an x-intercept, right? But what if we were to just bring that down, right? We just go -2. Notice here, oh, and you'd be like, seamlessly, it has an x-intercept now. Yeah, but that's because we shifted it down, right? But the basic shape of it and the principle of it remains the same, right? Because we shifted everything down. So now notice our asymptote is now at -2. So y is equal to -2. And that means our range would be also from -2 to infinity, right? See how that shifts? Our domain is still going to be the same, positive and negative infinity. But here we have a y-intercept of -1 and then a x-intercept of 1, right? So because we've just literally just shifted everything down. And then the same thing what if we do a +2? See how it goes up? Transformations, right? It was just translated up, right? And then but it's the basic idea. This point right here at this x-intercept is just going up and down this this axis here, so that's all we're doing here. So again, our asymptote is going to may change. It depends on what our situation is, what the equation is. But in basic, the basic look of it will look like this. Okay, just saying. So don't tell me later on, well, Miss Lee, did you tell me that the domain or the range was always 0 to infinity? And I'll be like, no, that is not what I said. All right, and now everything is recorded, so I have proof. All right, so here we go. So now this is end behavior. This is back to like unit 3 of what we did in quarter 1. So here we go. As x approaches negative infinity, so as we go more and more to the left, what is y doing? What is f of x doing, right? As we go further along, actually you should go this way, further along, we're getting closer and closer to the x-axis, right? We're getting closer to what? Not infinity. We're getting closer to 0, right? What? So that's what that's going to be. So it's getting closer and closer to 0. So that's why we have that at 0. And if we go the other way, so yes, so this y value is getting close. Oh, I went under, but it's getting closer and closer to 0. Whereas if we go on the other side, the more to the right we go, what are we doing? We're going up. So it is going to positive infinity here. And then are we increasing or decreasing? It is definitely increasing. And when does it stop increasing? Never. So this will always be increasing from negative infinity to positive infinity. It never at any point stops increasing. That is the whole idea of this. There'll be times when, well, in the very, if you go all the way to negative infinity, like that change, that growth will be so minimal, like you'll hardly tell. It's it's pretty much the same thing. It's very minimal difference, but it is slowly increasing. Just saying. All right, and so we're doing the same thing for the decay. Obviously, if the right one is growth and the other one's got to be decay, right? So notice it's going down. We always go from left to right, and so it's decreasing like this. And then, yep, domain and range, still the same. Still negative infinity to positive infinity. And then the range, and if you notice, it's still as low as it's going to go is at 0, and then it goes all the way up. Could it be 0? No, because that's where the asymptote is, right? That's the fence, right? Can't cross that. So that's going to be y is equal to 0. And then again, x. So notice all of these are exactly the same. None of them are different, right? Still no x-intercept, and our y-intercept is still at 1. So this is the point where they both of these guys share, right? Because b to the 0 power, whether it's positive or a fraction, is still going to be 1. Doesn't matter. So that is the power of 0. And then and notice our end behavior is going to be flipped because literally the shape has been flipped, right? So the more positive we go, that's when it approaches 0. And then the more negative we go, that's when it approaches positive infinity. All right. And again, this is since it's decay, it is intervals of decrease, not increase. So, and that is from negative infinity to positive infinity. Remember to always write down the negative number or the smallest number first, right? So there we go. Now we're moving into, excuse me, the exploration of E. We're introing it, and we didn't get too far. So we're going to finish it up the next time we meet. So here we go. So if you remember our original equation that we were talking about was A is equal to P, which was the principal, times 1, which was the 100%, plus the rate, whatever that rate that they're going to give us, right? And then to the T power. So here's Helen, and this is her situation. So Helen is opening her first savings account and is depositing $500. Suppose she decides on a bank that offers 6% annual interest, right? So this is their APR is 6%. We'll tell you that I don't think there's any bank that will offer you 6%. I'm just saying that, yeah, that you're not going to save a whole bunch of it. They're not going to give you that much interest in banks. It's very minimal, right? Because why? Because it's guaranteed that you're going to get that money, right? And so that's why people do stocks, right? Because, not that I'm recommending that for everyone. I'm just saying, because stocks will give you much higher percentage rates, right? But it's also more volatile. So it's more, you may lose money, right? You may lose money, or maybe, you gain a whole bunch of money, high risk, high reward, but also high losses too. So yeah, it's possible that you can lose it, but you can also get a lot more money, right? Like maybe 15%, maybe 10%. I don't know. Don't quote me on that. I'm not a stocks person. I'm just saying it's going to be higher than like what they offer you at the banks, right? Okay, so here we go. So write a function, A of t, to model the amount of money in Helen's savings account after t years, and determine the amount in the account after 1 year and 5 years. Okay, so 3 things that we need to do here. So first, we're going to write an equation, or a function, I should say. So here we go. So we got A of t, and remember our principal is P is 500, and our interest rate is 6%, right? You need to include the 100%. This is right here, the 1 plus 0.06, right? That's how we're getting 1.06. I just didn't include that extra step in there. I just did it in my head. All right, and then it's to the T power. Now we're gonna figure this out for the 1 and literally just plug in 1 for T, right? And you should get 530. If you don't, let me know. We need to work that out then. And then you do the same thing for 5 and you should get 669 and 11 cents. So after 5 years, how much interest does she have, that she get like for free, just by leaving her $500 in there? Almost $170, almost 89 cents short. I'll be like, bank, can you just give me 89 cents so that it could be even like 670? Yeah, probably not. You can always ask. Yeah, but they're going to say no. All right, so and so that's what that would be for 1 year if we get paid every, like at the end of the year. But what if, okay, so here, suppose that a bank decides to start compounding interest at the end of every 6 months. Now, compounding interest is kind of difficult to explain sometimes, well, maybe for me, or to understand, but I think of it as how many times are they going to pay me interest, right? How many times is that going to happen? And that's going to happen every 6 months. So that's twice a year, right? And so they're going to still offer the 6%, okay, per year. They only want to give 6% per year. So if they want to narrow that down to 6 months and 6 months, then how much percent would that be in 1 6-month time period? Well, that'll be in, takes the 6% divided by 2, right? You get 3%. So you get 3% the first 6 months, and then the next 3% the next 6 months. Okay, so so apparently Helen got some of her friends who are really good at math, or maybe not, I don't know, we'll see. John, Betty Jo, and Lizzie. Okay, and I said, can you please calculate this out? Help me out here. All right, so this is what they came up with. So, and again, take a look at this, and if you ignore the stars and the X's, right? We'll just pretend that they're not there. So as you can see, obviously, John and Betty Jo, we said that they were fine. They were good. So if you take a look at Lizzie's, right, she wasn't completely off, right? So she started with the 500, right, which is what she should have. And this is a 1 plus 0.03 because that's the, it was only 3% for that month, right? Or for that period, right? So that's going to be our 1.03 right here. So that seems good. But then what did she do? She multiplied all that by 2. And maybe that was because, because since we divided here by 2, then maybe we multiply it by 2, right? And then we get 1,300. Yeah, that's not how that's going to work. No bank's going to do that for you. You just doubled the money, right? You not only doubled the percentage, but you also doubled the 500, right? And where did the $500 come from? Not from the bank, right? That was from Helen, right? So they're not trying to double whatever you deposit, right? That's not what's going on here. So yeah, that's why Lizzie's is not correct. I would like Lizzie's to be correct, but it's not, right? So if you take a look at this, so John did it like this. He kind of like did it step by step. So 500 months, this is exactly the same as Lizzie's, right? 1 plus 0.03, right? So this is the 1.03 right here. And that's gonna give you at 6 months, $515. So now what we do is notice that you take that $515, not the original $500, the new balance, right? And we're gonna multiply that by 1.03. Okay, and so then you get $530.45. Okay, so notice that that didn't just double the, the interest, because remember that's a $15 interest, and you like to, just double it, that's 30. Is $30.45. And some of you guys may be like, well, that's just 45 cents, like whatever's, right? But I mean, that's 45 more cents that you didn't have. And remember, that balance is we're gonna take now 3% of that balance, right? And you can actually get more money that way if you're compounding it twice a year as opposed to once a year. Not by much, it's like 45 cents, right? But still, it's still more. Could you imagine? What if it was, instead of $500, it was like $1,000 or $10,000, right? Then that difference will be, bigger, right? So literally what we're doing is we're taking the 500 times by the 1.03 and then times that by 1.03. So literally, how many times are we multiplying by 1.03? And if you can see Betty Jo here, that's exactly what she does. She's like, well, that's just doing that twice. So here's the 1 plus. Notice she showed the work here of how she got 0.03, right? So it's the 0.06 divided by 2, which would be 0.03. And then square that. So she's just squared that and then multiply by 500. And since it's multiplication, it does not matter which order you do it, as long as you do all of them, like multiply all of them, right? So yeah, and if you notice, her answer is the exact same thing as what John got. All right. So, and I know I said I was going to do this in the video, but I'm actually going to save this for next time we meet for our lesson. Okay. But this is where it gets interesting, because the question is, well, if it's better to do it, compound it twice, then what if we compound it like every month, right? Then wouldn't that be better for us, right? Then think about it. So what would our percentage look like each month, right? Because if we take that 6%, we initially divide it by 2 because we're going to get paid twice a month, twice a year, right? But if it's every month, what would we divide that by? I'll leave you with that. All right, have a good one.